Okay, so far for our physical applications, we've seen how to compute the work done in stretching springs, compressing springs, pulling things with ropes and cables, maybe things with some leaking buckets of water or concrete or whatever, or sand. But now we got to talk about what happens when we want to pump water out of a tank. This is a common thing, right? You want to make sure you have a powerful pump enough for like maybe for your swimming pool or maybe for, I don't know, a water tower or something. And we got to figure out the amount of energy required to pump all the water into or out of a vessel. So let's just go ahead and get started. So we have one problem with this, okay? So we have a tank and it's in the shape of an inverted cone. So let me go ahead and draw that tank here. Okay. The height of this cone is 10 feet. And we have a radius of 6 feet. So there's the center of the cone, and the radius is 6 feet. All right. The tank is filled to a depth of 8 feet to start, so let's go ahead and draw in this 8 feet here for the water. And water is pumped over the upper edge of the tank until 3 feet of water remain in the tank. And so here, let's say that's 3 feet here. How much work is required to pump out that amount of water? And we're given this very important item here that the weight density of water is 62.4 pounds per cubic foot. Okay, that's what it is in, sadly, imperial units. So that's going to be our weight density rho. Okay, this funny looking P here. Okay, and just a quick remark here. Okay, we'll see this in the next problem when we do part 4. But in the next problem, if you're going to be doing this in metric in SI units, the weight density of water is 9,800 newtons per cubic meter. Okay, those quantities will be given to you, okay, because you need to determine the weight density of the fluid that you're working with. All right, so this one really takes a bit of setup here. It's not set up exactly like our usual work problems, where we have to find the energy required to, say, lift an object or compress a spring, but the energy here is just in pumping water. So there's a bit of setup that we have to do here. So in this light blue color here, let's go ahead and consider, say, well, first let me go ahead and draw the axis of the cone here. Okay, just down the center. And let's go ahead and draw in, say, one little marking of water here. Okay, let's say this is a bit of water at some level here. And the idea is we want to approximate this by a very thin cylinder. Okay, so there we go. This is a little bit of water here. And we also have to set up our coordinate system as well here. And the convention that's done in the text is, oh, one of my classmates just walked by. The convention that's done in the text here is that we're going to set our coordinate system so that here at the top of the tank is going to be y equals 0. And if we're going downwards, that's the plus direction. Okay, for those of you that have taken Physics 1, you may need to remember, right, that in some problems you need to set up a coordinate system that makes sense with your problem. For this problem here, just so that some of the geometry works out, we need to set our coordinate system so that the top of the tank is 0 and going down is the plus direction. All right, so now let's do a few more measurements here. Let's say that this little slab of water here in the light blue is, say, y feet from the top. Okay, so that's going to correspond with a depth of y. Now, if it's at a depth of y, how much water is remaining in the tank? Well, the remaining distance here is 10 minus y. 10 minus y. Let's see if I can do this sideways here. 10 minus y. There we go. All right. Now, we need to figure out what the volume of one of these little slabs of water is, okay? Now, the thing is, since this is a cone and not a cylinder, the radius changes at every level. So the way that we determine this is using the properties of similar triangles. Okay, so I'm going to go ahead and highlight the two triangles that we have here. In red, we have this big triangle formed by the axis of the cone, the radius at the top, and then the slant length down here. That's this red triangle. And then we also have this green triangle here. Okay, so we're going to use some ideas from classical geometry. Okay, we're going to build some ratios to look at these widths here. So let's go ahead and give these things some names. I'm going to call the radius here r. Let's just do that in the same color. This radius is r. Okay. And we know the depth at that point, or rather, the distance from the slab to the apex of the cone at the bottom, that's 10 minus y. So we have the following ratio. Okay, so we're going to use similar triangles. Okay, if I can spell. Spelling is hard on your birthday. Similar triangles. Okay, so what do? Well, we have the red triangle. We know that the radius 6 is in proportion to the height 10. And for our green triangle, okay, the small triangle that is where our slab of water is situated, we have the corresponding radius r, okay, in ratio to the distance to the apex, 10 minus y. So let's go ahead and look at what we have here. In red, okay, we have the ratio of the radius to the height, that's 6 to 10. And then in green, the ratio of that radius to the height, r to 10 minus y. So our proportion here, we have 6 is to 10 as r is to 10 minus y. Now we'll go ahead and solve for r. Okay, let's go ahead and solve for r. So do some cross multiplying here. You can even reduce that fraction on the left-hand side. Super easy here. We get that 3/5 times 10 minus y is equal to r. So we now have an expression that tells us the radius of one of these little slabs of water, these pucks of water, at any depth y in relation to its distance from the apex at the bottom. All right, so now how do we actually go about doing this? Well, let's go ahead and first compute the small volume element here, okay? So we'll approximate this by a cylinder. Okay, so let's go ahead and like draw out what the slab of water would look like. We have some sort of radius here. And if we draw these like very thin enough, say with some thickness delta y, okay, I have a radius here. Okay, well, how do I find the volume of a cylinder? Well, it's just pi r squared times the height. So the volume elements here, which I'll call delta V, the volume element, the volume of one of these small slabs of water, is going to be pi times the radius squared times our thickness delta y. But what is r here? Well, we just computed it above. Okay, we have this right here. So we have pi times r squared. So let's go ahead and write that in. 3/5 times 10 minus y squared times delta y. Okay, and after doing a bit of, shuffling and exponent rules, we have that the volume element here, delta V, is 9 pi over 25 times 10 minus y squared delta y. So that's the volume of one of these slabs. Okay, now we're going to build the next step here. Okay, we're going to go from a volume to a force, okay, the weight. Okay, so I'll go ahead and do this in black here. Or actually, rather, let's do this dark blue here. So go from volume to weight, okay, the force on this object, delta F, okay, on this small slice. Now let's think about the units here. The volume is in length cubed, in cubic feet. But our weight density is in, well, in this case, pounds per cubic foot. And pound is the unit of force in the imperial system. So how do I get rid of those cubic feet? Well, I need to multiply by another volume object, right? So the idea is we're going to take our delta V here and multiply it by our rho here. Okay, so after we do everything, remember above rho is 62.4 pounds per cubic foot. So we're going to use that here. So we take our item here, 62.4, that's our rho, and then times, let's see, 9 pi over 25 times 10 minus y squared delta y. Now, that is the force required to lift this object over the top of the tank. But now, how far does it have to travel? Let's go back to our picture. All right. If we look at our picture here, we see that this little slab is at depth y feet. So it has y feet to travel. And so in that end, if I can go back to the correct position here, to that end, okay, For work here, the work required to lift that small element, delta W, okay, is going to be our force times the distance. So it's going to be y times delta F. Force delta F times distance y, okay? And so now putting everything together, we get 62.4 times 9 pi. And then we have y times 10 minus y squared delta y. So that's the work to lift one of those small slabs of water. Now, I need to lift all the water out, so I need to sum up all these tiny pieces. Well, if I'm summing a bunch of tiny pieces, that's how we define the definite integral. Okay? Think about this approach of going from small to big, okay? So, the total work done, okay, let's go ahead and think about this. Let's set up the integral, and then we'll get the limits of integration. So the total work required here is, so I'm just going to integrate this thing here. Okay, I'm going to integrate both sides of this thing. Okay, so the total work here, the scalar, 62.4 times stuff, I can just put outside the integrand. And then we're going to have an integral, y times 10 minus y squared dy. So that's the integral that represents the work needed. Now, are we lifting all the water out of the tank? Well, let's go ahead and check here. All right. Right now, the tank is filled to a depth of 8 feet, okay? So if it's filled to a depth of 8 feet, all right, let's go ahead and mark that in here. So if I'm starting at 8 feet, okay, that's this line right here. Here we're going from y equals 2, okay, because there's 2 feet left to go, to y equals 7. And that tells you the limits of integration. All right, so let's go down here. So now our limits of integration, we're going from 3 to 7. So it looked like there was a lot of, no pun intended, work to set this up, but in the end, take a look at what you have. The integrand is a polynomial. So all you have to do is just expand the polynomial first and then use the power rule. So let's go ahead and do that here. So again, we still have that scale factor out front. And then we're going to have the integral from 3 to 7. All right, let's go ahead and expand. So use the F word, not that F word. 100 minus 20y plus y squared dy. All right. And now we're going to multiply that y into the parentheses there. Okay, again, just usual distributive property. Let's go ahead and write out this number again. Only a couple more times that we have to do this. Okay, so this is the integral from 3 to 7 of 100y minus 20y squared plus y cubed dy. All right. And now, what's our final step here? Well, our final step is going to be the following. Let's kind of up the power here. All right. So, what do we need to do here? Just use the power rule, right? So we have that funky number. Okay, 62.4 times 9 pi over 25. Okay, and now we're going to find an antiderivative. So we just use our power rule stuff here. 50y squared minus 20y cubed over 3 minus y to the fourth over 4. We're going to evaluate this on the boundary, 7 to 2. Now, you can go ahead and use your favorite calculating tool for this. I went ahead and put this into both MATLAB and Python. And it turns out that we'll get a number, something like 43,255 foot-pounds of work. Okay, and that's all there is to it. So let's go ahead and recap the process here. Okay, we have to draw our picture. Okay, make note of any measurements that we have. Then we build up these two similar triangles here that I've colored in red and green. Build your proportions, solve for the radius, and then build your relationship for the volume of a slab, the weight of such a slab, the work to lift such a slab, and then you get the total work, and you get a number, just like that. All right. So this one can be challenging, but if you go ahead and outline your process and look at a lot of other examples that you've worked in class, and of course from the text as well, you'll be able to get these. the principle is still the same. Find the force, find a distance, and you're ready to go. The numbers may be a little scary, so to say, but that's because we're working with some physical units here, okay? Now, the last part, we're going to do something similar, but now we're instead going to look at hydrostatic force, okay? We have things pushing it against the side of a tank. So we want to make sure that we construct some things that are able to hold these fluids, right? We don't want any weird spills happening here. I'll see you in the next one.